Welcome to my classroom. In this fluid and particle mechanics, particularly in this module, we have been discussing about macroscopic momentum balances and microscopic momentum balances. We have seen the control volume concept, we have discussed about Eulerian description, and we have discussed about Lagrangian description, and we have seen the difference between them, and we have discussed about velocity potential, and we have solved a few numericals on it also. Well, to start fluid dynamics, we are going to start with Newton's second law. Before that, I hope you recall we have defined few terms like path lines, streak lines, streamlines, stagnation point in the previous lecture. So what is that path line? So we know that it is the trajectory traced by an individual fluid particle over a time during its flow. What is streak line? So these lines represent the positions of fluid particles at a specific instant of time, whereas streamlines they indicate the instantaneous direction of fluid flow at a given point. So because this Bernoulli equation or Bernoulli's theorem is defined over a streamline, so that we are going to discuss. So it's important that you go through the definitions of path lines, streak lines, streamlines and stagnation points one, and we should know their applications. For example, path lines, they are used for studying the historical behavior of particles in a fluid flow, whereas these streamlines they are used for visualizing the flow patterns created by injecting some tracer or dice into a system, whereas streamlines are applied in fluid mechanics as well as aerodynamics for flow visualization and analysis purposes. So actually these path lines describe the actual paths followed by individual fluid particles over time. Streak lines represent the collection of fluid particles that have passed through a specific point over a certain time duration. It's providing a snapshot of a fluid pattern at a particular moment. Okay, the stagnation points, they are locations where fluid velocity is zero or nearly zero, so which often occurs around any obstacles or within the boundary layers. So they are also important to understand the fluid behavior under these areas. Okay. Now let's move on to energy equation, that is Bernoulli's equation. Okay, so before deriving Bernoulli's equation, we will derive Euler equation for streamline. On integration of this Euler equation, we are going to get Bernoulli's equation. Okay, so in this next 50 minutes, we are going to look into the statement of what is Newton's second law, like net force, summation of net force is equal to mass into acceleration in particular direction. Then we are going to substitute various forces and we are going to make some assumptions, reduce that force terms to minimum two terms like force due to gravity and force due to pressure alone. Then we will consider a cylindrical element in a fluid streamline. Then we will make the force balance and we are going to consider three forces. One is force acting on the upstream side, force acting on the downstream side, and component of the weight, and we will make the balance and we will simplify to get the Euler equation for a streamline, and upon integration we are going to get Bernoulli's equation. So before deriving the Bernoulli equation, we are going to look into what are the various assumptions that we are making to derive that Bernoulli's equation, and towards the end we are going to discuss about the limitations of Bernoulli's equation and what is the need for modified Bernoulli's equation and how work done on the system and major losses are taken into account in the modified Bernoulli's equation. So this is going to be the agenda for this lecture. Please, I request all of you to write it on your own notes and try to do the derivation as a practice. Please be ready with your notebook. Let's start this fluid dynamics. Ready?
What is fluid dynamics? In fluid dynamics, forces are also taken into account. That means, so far we have considered only in fluid statics, the velocity was considered to be zero. In fluid kinematics, velocities are taken into account, and in fluid dynamics, we take into account of the forces that is acting on the fluid that is flowing. So, according to Newton's second law, we have that net forces acting in a direction net forces that is acting in a particular direction is equal to mass into acceleration in that particular direction. So we have this as mass into acceleration in that given direction. Okay. So in this particular treatment, we will consider certain forces. So for that, I'll give you a short term, like you know about VGP Golden Beach. It's there in Chennai, and we know one of the leading software companies in India, TCS, Tata Consultancy Services, right? So VGP Golden Beach and TCS. So we are going to consider some six forces here. I'll let you know what are those forces. That means here we are going to consider FV plus FG plus FP plus FT plus FC plus Fs. So some six forces we are going to consider along this particular direction. Let me say X equal to M into A into X. Okay. So now let us see what is that VGP and TCS stands for. So when I say that, any guesses there? You can say that V for viscous force. Okay. We have V for viscous force, and we have this G for gravity force, force due to gravity. So you have gravity force, then you have pressure force, force due to pressure. And what is the TCS stands for? T for turbulent force. It is force due to turbulence. Okay. Then we have C for compressibility. We have compressibility force, and S for any guess? Yeah, it's surface tension force. So we are going to consider some of the forces. You see, apart from that, there are inertial force, buoyant force, like that. So here we are considering six major forces that will be acting on a flowing fluid. One is viscous force, gravity force, pressure force, turbulent force, compressibility force, surface tension force. Okay. Now, so among these six forces, if we write that, we can write, we have already written that. Okay, let it be equation number. Let it be equation number 1. Okay. Now, if we consider that very high velocity, when you say it is a very high velocity, what we can consider is that surface tension forces will be negligible, right? So we can have, when the velocity is high, when you say V is very high, when you have very high velocity, we have that we have that F due to surface tension is equal to 0. And if we consider incompressible fluid, if the fluid is incompressible, what will happen? So we have that force due to compressibility equal to 0. Okay, so if we can substitute these conditions in equation number 1, so what we get is that among the VGP TCS, C and S will get cancelled. So only we have FV plus FG plus FP plus FT equal to M into, if this is in X direction, we have M into A into acceleration in x direction. Okay, so let it be equation number 2 now. So we can further, this equation is actually, this second equation is called as Reynolds equation of motion. Reynolds equation of motion. Now we can further moving forward. So what will happen to Ft? What will happen to this Ft if it is laminar flow? We can say for a laminar flow, for a laminar flow, force due to turbulence will be equal to 0. Okay. So now this equation gets reduced to simply three major forces, that is F due to viscous, okay, plus force due to gravity plus force due to pressure of the fluid is equal to m into ax. Let it be equation number 3, and this equation is called as Navier-Stokes equation. Okay, this equation is called as Navier-Stokes equation. Now, this equation number 3 can be further reduced to write if this, what if it is an inviscid fluid? Okay, that is, what if it is inviscid fluid? Inviscid fluid means it's a non-viscous, that is zero viscosity. For a zero viscosity fluids, what is that when we say that zero viscosity? It is actually ideal fluid, right? So for ideal fluids, remember no such fluid exists, but to understand these flow behaviors, we always start with these ideal conditions. Okay, so for ideal fluid, we have that F viscous equal to 0. Okay, we have F viscous equal to 0. So if we substitute this condition in equation number 3, so this equation number 3 will get reduced to simpler form Fg plus Fp is equal to, so this is in particular direction x, is equal to m into ax. Okay, so let it be equation number 4, and this equation is called as Euler's equation of motion. Euler's equation of motion. You should know that for ideal fluids, what will be the Reynolds number value? Can you recall? So we know that mu is 0, that is viscosity is 0 means Reynolds number is rho Vd by mu. So when denominator is 0, the value of Reynolds number becomes infinity. So Reynolds number for ideal fluid is infinity. So you recall that one here. So this is what we get from basically considering Newton's law of viscosity. So far what we have done. So we have considered this fluid dynamics, and as I told you, in fluid dynamics, we take into account of forces that is acting on the fluid, and according to Newton's second law, we have net forces acting in a particular direction is equal to m into acceleration in the direction. So we have mass into acceleration in particular direction. And for net forces, we consider six major forces, that is viscous force, gravity force, pressure force, force due to pressure, force due to turbulence, force due to compressibility, and force due to surface tension. So among these six, when you slowly consider specific case, like when velocity is considered to be very high, then surface tension, effect of surface tension is negligible, and we consider the fluid to be incompressible, particularly for liquids. We have compressibility force equal to 0, and the six terms becomes four term in the left hand side. So then we consider that particular equation is called as Reynolds equation of motion. And if we can further consider The case of a laminar flow, then force due to turbulence becomes 0. So that again that equation comes down to Navier-Stokes equation form. We will be writing that actual force terms, and if you are able to write that, we have another form of Navier-Stokes equation that we will discuss separately. Now, when you consider another case of if it is an inviscid fluid, that is zero viscous fluid, that is when you consider an ideal fluid which is inviscid, then viscous forces are also zero. So which makes this equation to simplify into the form of Fg plus Fp equal to m into acceleration. Okay, so this equation we will see that one. Okay, now we will move on to important equation, that is the energy equation in fluid mechanics, that is Bernoulli's equation. In fluid particle mechanics lab introduction lecture, in the lab demonstration video, we have discussed about introduced this what is Bernoulli's equation, what are different energy forms or head pressure head form. We can write that on all that we have discussed. So again, I will recall it here. What's Bernoulli's equation? Actually, one Swiss scientist Bernoulli observed that along a streamline in our class lecture, we have seen what is the definition of stream, path line, streak line, streamline. Everything is defined in the past few lectures in the class. Okay, so along a streamline, total energy is constant. Along a streamline, total energy is constant. So this is what Bernoulli has observed, which can be written in pressure head form as P by rho g plus Z1 plus V1, when you say P1 by rho g plus Z1 plus V1 square by 2g is equal to P2 by rho g plus Z2 plus V2 square by 2g. So where when you have a consider a cross section area at section A1 and you consider another cross section area 2, so which are separated by a height Z1 and Z2 is the difference level. Let at this point 1, let the pressure acting is P1, velocity be V1, diameter be D1, and at this section 2 we have pressure P2, velocity V2 and diameter D2. Then what we have is P1 by rho g plus Z1 plus V1 square by 2g equal to P2 by rho g plus Z2 plus V2 square by 2g. This is what Bernoulli's equation states. Okay, but while saying so, while this equation makes some of the assumptions. Okay, so this equation makes some uh, fundamental assumptions are made in this equation. So we should start with assumptions made. Assumptions made in Bernoulli equation. So what are the assumptions made in Bernoulli equation? We should able to list it out. Okay, so with that only we always start this derivation. Okay, so we first assumption made is the flow is steady and continuous. Flow is steady and continuous. Also, flow is uniform and incompressible. Okay. So other assumptions are about the fluid. The fluid is inviscid. That means what? The viscosity is zero viscosity fluid. Okay. And some of the other assumptions are the average velocity of the cross section is considered. Average velocity is considered. Average velocity of the cross section is considered. And another important assumption made here is flow is along the flow is along a streamline. We have seen the definition of streamline. What is streamline? An imaginary line along the flow path of a fluid particle. The point at the tangent at any point will give the direction of the velocity at that point. Okay. So we have flow, and apart from that, we assume only two major forces which are acting. In this case, we consider are no forces other than no forces other than gravity and pressure are acting. Yes, you have seen that. We have, if you look here, we have reduced it down to only two cases, right? What are they? Oh, here. So you have gravity force and pressure force. So when you come down to this equation level, so we are considering only two forces, that is gravity, force due to gravity and force due to pressure. Only these two F's are acting. When you go move on to derive this Euler equation, which is part of this Bernoulli's equation. Okay. So what are the two F's which are important here? Gravity forces and force due to pressure. Okay. So these two forces are predominant here. So what we have listed, I repeat, we have made some assumptions. We have considered the flow to be steady and continuous. The flow is uniform and incompressible. The fluid is inviscid, that means that viscosity is zero. And we are going to consider the average velocity of the cross section, and we have the flow is along a streamline because Bernoulli equation is defined. The total energy is constant along a streamline. So that way, that also we are assuming, and we assume that other forces are negligible except the force due to pressure and force due to gravity. Okay. Now what we will do? We will consider a streamline. We will consider a streamline in which a single cylindrical fluid element we are going to consider. So along a streamline, we are going to consider, okay. So we are going to consider a small cylindrical element, okay, and let it be this middle section, okay. So which has a length of ds. What is ds? Is the length of the cylinder, and have a cross section area dA, okay, cross section area. So this is going to be the same on both ends, okay. Let P be the pressure. P is pressure. Okay. Let dz is the height. Okay. So let dz be the height of the cylinder. Dz is depth. Let me say height. Okay. So what we are doing? We have considered a streamline in which a cylindrical fluid element with a particular mass is considered, which the cylinder is having a thickness of ds and is having a cross section area of dA. Okay, let the mass of this cylindrical element is m. Let m be the mass of the cylinder. Okay, so this mass of the cylindrical element is this one. So we know by definition of mass density. Mass density. Well, you know what is the definition of mass density? What is that? Mass density rho is equal to mass per unit volume, right? So what is m then? M equal to rho into v. This is volume, right? So m equal to rho into v, And what is the volume of the cylindrical element? Cross section area is dA. Okay, cross section area is dA and length is ds. So then what is the volume? Volume of the cylindrical element is ds dA. Okay, so we have this mass of this cylindrical element equal to rho into ds into dA. Okay, now what is the weight of this element then? Weight of the cylinder. Weight of the cylinder is, what is the weight of the cylinder? What is the weight of the cylinder? So we know that m equal weight equal to m into g, right? Weight is m into g. Okay, so we have w equal to m into g, which is rho g ds dA. So this is our w. Okay, now we have written what is w. Let's move on to what is velocity. What is the velocity along this component x this particular direction? Let us say velocity along this velocity along s direction. So velocity along this s direction is ds by dt. ds by dt. Okay. I repeat. We are writing the velocity along this particular direction, s direction, that is tangential direction. Along the tangential direction in s. So we have velocity equal to ds by dt. Then what is acceleration? Then what is acceleration? Acceleration is dv by dt. Okay, so which can be written as dv by ds into ds by dt. So we are multiplying by ds, no? So it can be written as v into dv by ds. Any doubt in this? So acceleration is again rate of change of velocity. So dv by dt. So here we are what we are doing, multiplying and dividing by ds. We are getting this expression. So we are multiplying here, dividing here and multiplying here, which will take care of this to be the same. So we have dv by ds as it is, and for ds by dt we have v, so that we are writing here. So this is replaced by v, so that v is coming over here. Okay, so now we have written what is velocity, what is acceleration. Okay, so three terms we are going to make use. Let it be v. What is the v we have written? Written what is v, and we have written what is acceleration. Okay, why we have written that? We are going to substitute them in the equations. Okay, and similarly I am just preparing the things what and all we are going to substitute in our major equation. Okay, so that we will go bit more. I am just preparing you to know what and all different terms we are going to make use. Okay, now if we say if this is our w. Okay, this is w and this is theta. And what is this along this component of W? What is this component of weight along tangential direction S? So for that we should know that this is W. What is this? Okay. So we know that cos theta equal to adjacent side by hypotenuse. So you have this adjacent side equal to hypotenuse into cos theta. Okay. So what is this one? So W into cos theta. Okay. So what is this W into cos theta? So we have W into cos theta, weight component equal to. So because actually we will be writing this thing. So if you take okay, so if this is theta, so we have what is hypotenuse here? Hypotenuse is W. Okay. So you have hypotenuse equal to W. Mm, so this is your adjacent side weight component in S direction. I can say weight component in S direction is equal to W into cos theta. Okay. What is cos theta here? It is adjacent side which is WS divided by W. So we have adjacent side WS equal to W into cos theta. Already we have written what is W. What is that? Rho G ds dA. Okay. So we can write WS is equal to rho G ds dA cos theta. Okay. We are going to make use of it later. Fine. Now we have to go back to this original diagram now, where the fluid element is considered. Yeah. So we are considering this one, right? So we have to consider that we have seen that let P is the pressure acting on dA. Okay, pressure. Let P be the pressure acting on the side dA at this side Z1. Okay. So what we have is force. We can write what is the force acting on this point. Okay. So here let F1 be the force acting at this point. Let F2 be the pressure force acting at this point. Okay. So we have to see. So here the force will acting on this direction. Here the force will be acting like this. So let me write all the forces that is working on it here. So what we have is force at A1 is equal to F into dA. Okay. So this is direction. What is the direction of this force acting? What is the direction of this force acting F1? So this is along the S direction. Okay. Then what will be the F2 here? This is P into A, sorry. Okay. So now we are going to consider let P is the pressure acting on this one. Okay. So then what will be the force acting on this direction is F equal to, that is F1 is equal to P into dA. Okay. This is along S direction. This is along S direction. Similarly, what is that F2 here? So here it is going to be P plus dP. Okay. That is P plus dP. And this is along S direction. No? So for simplicity, for evaluation purpose, we write this into dA. Okay, so this is the force acting because this is P. Here it is P plus dP. And for derivation purpose, we write taking like derivative dp by ds into ds, because ds cancel. We have simply p plus dp without changing meaning. So we have p plus dp by ds into ds is a pressure, and this F2 is equal to multiplying by this cross section area, which is dA again. Okay, here also area is dA. So we have F2, but remember this F2 is acting along S. This is your S direction, right? So this is opposite to S direction. So it is opposite to S direction is the direction in which this F2 is acting, which is equal to P plus dp by ds into ds into dA. Okay. And what is the another force which is acting? That is W value which we have calculated. That is component of W. What is that? Component of W is Ws. Okay, so totally now we are having only three forces, net forces in the left hand side, because we are going to start with net force along S direction is equal to M into A into S. Okay, so this according to Newton's law. Okay, now what we have is P into dA minus P plus dp by ds into ds into dA, these two forces, and along this also component of weight which is acting. So we have, if we have taken this element, so this side we have F1, this side we have F2, and we have Ws, which is again minus direction. Okay, so the component of weight of this element is x minus 2. So minus Ws is equal to m into A into S. Okay, that is the tangential direction. So what we have is this one. So I can write P into dA minus P into dA minus dp by ds into ds dA minus rho g ds dA cos theta, which is equal to m into acceleration. Okay, so we have already written what is m into acceleration. Can you take it from there? Third point, v into dv by ds. Any doubt in that? V into dv by ds. Okay, so m also we have written. What is that? M equal to rho into ds dA. Okay, and what is as? As is v into dv by ds. Okay, so now in this I repeat what we have done. So we have considered only two forces. One is pressure force and gravity force. These two are the only forces which are acting as per the assumption. So we have written the force acting in the upstream side of this cylindrical tube. Here the force acting, and similarly the force acting on the other side. So this force is along the direction of the flow, and this one is opposite to the direction of the flow. Similarly, the weight component is also opposite to the direction of the flow. Okay, so that way they are written with minus signs. Okay, so the net force is PDA minus this force acting on this F2 minus weight component Ws. And M is, we have substituted what is M, that is density into volume, acceleration, velocity into dv by ds. Okay, so these all terms we have simplified and derived, and now we have substituted them directly here. So this term will get cancelled. Okay, so we have this PDA minus PDA getting cancelled, and if we, what we can observe another thing is, in all the terms we are having dsda. Okay, so we can divide by dsda. So that is, we are dividing by volume throughout, volume of this one. So what we have is, minus dp by ds So the first term is minus dp by ds, okay, minus rho g cos theta is equal to rho v dv by ds. Okay, so now we will replace this cos theta also. Okay, so what is this cos theta? Cos theta is again nothing but dz by ds. Cos theta is nothing but dz by ds. Okay, because if you consider this ds, okay, dz, so this is the theta. So you have, so we have cos theta equal to dz by ds. Okay, so that also we can substitute here. Okay, so if you substitute that one here, so what we have is minus rho g. When I substitute cos theta, we have dz by ds minus dp by ds equal to, minus is there, no? Equal to rho v dv by ds. Okay, so now what we see is all can be taken to one side. So we can write rho v dv by ds plus rho g ds by dz by dou s plus dp by ds is equal to 0. Okay, so now we can multiply throughout by ds. So what we get is rho v dv plus rho g dz plus dp is equal to 0. Okay, so this is the final equation what we get, and this equation is called as Euler's equation for a streamline. Okay, this equation is called as Euler's equation for a streamline. So what we are going to do is, if you are able to integrate this Euler's equation for a streamline, we will get Bernoulli's equation. If we integrating this Euler equation, we are going to get Bernoulli's equation. So how we get Bernoulli equation? By integrating. By integrating Euler's equation, we will be getting Bernoulli's equation. Okay. So what we will do? So take this equation. So we have this equation. Okay. So what we have is rho v dv, rho g dz plus dp equal to 0, which is Euler's equation. So what we will do is we will integrate them. Okay. So how do we integrate it? If we take integral, so integral, I'll change the color. Yeah. So integrating rho v dv plus integrate dp plus integral of rho g dz equal to 0. So by integrating 0 on the right hand side, what you will get? You are going to have a constant term. You know that if you take the derivative of constant, it will become 0. If you take integral of 0, it becomes a constant. Okay. So now, so if you consider, we have considered this assumption. According to our assumption, density changes are negligible. Okay, so we have rho is taken outside common. So integral v dv plus integral dp plus this rho g is staying outside equal to constant. Okay, so now, so what we get is rho into rho into v square by 2 plus dp is p plus rho g z equal to constant. Okay, so this is what we get. And if I take for a standard form in pressure head form, I want to write it in head form, means a pressure head form. Divide by rho g throughout. Divide by rho g throughout. What we get is p by rho g plus z plus v square by 2g is equal to some other constant. Okay. Don't say constant by rho. Okay, we get constant by rho g, some other constant. Okay, so dividing by rho g throughout. So what we get is this one. So here I can say this P by rho g is called as pressure head. We have defined that pressure head, right? This is the definition of pressure head. So this is called datum head. This is called velocity head. Okay. So we have three terms here, which is having the derivation. So we have derived this equation and we have P by rho g is the velocity head. Sorry, P by rho g is pressure head. Z is your potential head or datum head. Okay, so you can also call it as potential head. It's also called potential head. Okay, and if you are dividing this equation by mg, what do you get? When you divide by mg, what do you get? Sorry, if you are multiplying by mg, when you multiply by mg, what we get is pm by rho plus mgz plus mv square by 2 equal to constant. So what you are having in terms of energy, you are having this. What is m dot by rho? M dot by rho is your V. So you have PV plus mgz plus me square by 2 equal to constant. Okay. So now you have all this energy. So in terms of energy, we have these two. Okay. So we should be aware of the limitations of these Bernoulli equations. Now we have derived the equation. We should be aware of the limitations of this equation. What is that? It doesn't consider the viscosity is, this assumes that viscosity is equal to 0. That means when mu x is, it's not taking into account of resistance offered by to the flow by this viscosity, right? And similarly, actually it is considering uniform velocity, right? But we know that velocity varies even if in a laminar flow, the velocity will vary from 0 to infinity along this along the cross section, right? But what we are using here is average velocity only. Okay. And similarly, it's not taking into account of any external forces. No external forces are considered. Okay, but actually, in case of a reality, we are going to have frictional force acting, right? That means there will be major losses and minor losses. Major losses due to final so friction loss. Okay, and also we are going to have minor losses, which may be due to fittings or any other obstacles. Okay, and remember this type of frictional loss energy, there will be loss of energy in the form of heat, right? So they are not taken into account here. Okay, so there are no, if even some work done is by the pump. Okay, so if any work is done by the pump, that is also not considered into this Bernoulli's equation. Okay, so these are some of the limitations of Bernoulli equation. So there comes a need for modified Bernoulli's equation. What is that? So along with this is total head equal to constant. We are going to take into account of, let me say, total energy at location 1 is considered, right? Similarly, total energy at location 2 is considered, right? So in modified Bernoulli's equation, any work done by the pump is taken into account in the left hand side plus any losses are considered in the right hand side. So there comes the modified Bernoulli's equation, which can be written as P1 by rho g plus Z1 plus V1 square by 2g plus head developed by the pump is equal to P2 by rho g plus Z2 plus V2 square by 2g plus H loss. This H loss takes into account of H loss due to major loss, that is friction, and loss due to minor losses, that is loss due to fittings. Okay, so this equation is called as modified Bernoulli's equation, and it finds application in various engineering applications. And there are so many equipments or devices which are used to measure the velocity or the volumetric flow rate, which are devised based on this Bernoulli's equation. So in the next lecture, we are going to discuss about applications of Bernoulli's equation. Particularly, we are going to focus on venturi meter and orifice meter, two flow measuring devices which are widely used in fluid flow. Thank you so much for listening to my class. Catch you in the next lecture. Bye bye. I repeat, this modified Bernoulli's equation takes into account of head developed by the pump in the left hand side of the equation, and all the losses like major loss and minor loss is considered in the right hand side of the equation. So thus we have a modified Bernoulli's equation given by P1 by rho g plus Z1 plus V1 square by 2g plus head pump plus P2 by rho g plus Z2 plus V2 square by 2g plus H loss.
Well, in this lecture, we have derived Euler's equation, assumptions made in Bernoulli's equation, derivation of Bernoulli's equation, limitations of Bernoulli's equation, and the need for modified Bernoulli's equation to take into account of work done by the pump and the major losses that occur in a pipeline. Thank you so much for joining my classroom. Meet you in the next video. Bye bye.